anybody's new, I'm Alan. I'm the chairman of the Hertford Astronomy Group. We welcome you to this meeting. The format of the meeting is that after my introductions here, we pass over to Martin, who will talk to you about the forthcoming night sky. After Martin has given his talk, we'll pass you over to Jerry, and Jerry will introduce tonight's speaker. Now, we're really privileged with our speaker. He's actually said that his talk, last time he gave it, lasted an hour and a half. So we're in for a really great evening. There will be an opportunity to ask questions at the end of that, and we would ask if you could use the chat facility to do that, so that whoever's hosting that particular area can look at the questions and present them to the appropriate person. And of course, you can use the chat facility if you want to talk to any of the other members who are with us this evening. Following the main talk, I will wind the meeting up by telling you about a couple of future events that are happening, and that's the whole of the evening covered. I would imagine we're going to finish somewhere between about 9:30 to 10 o'clock. So, if I can ask if anyone, if you could make sure you mute your microphones while the speaker is talking, that would be much appreciated. I think my co-host might be able to mute everybody as well.
I'm doing it now.
So if he does hear strange noises, he may intervene. So that's enough from me. I'm going to pass you over now to Martin, who's going to talk about the night sky in the next few weeks. So over to Martin.
Thanks, Alan. Good evening, everybody. Sorry I've not been here for a few months, but I got the dreaded COVID, unfortunately, so wasn't up to doing talks, but fully recovered now. So I shall try and give a little talk on the night sky. So that's not a good start. Okay, right. So first of all, just to say, been quite disappointed the viewing currently, because there's still somebody unmuted. I don't know who it is. I keep busting through. If make sure everybody's muted, that would be useful.
I think, yeah. There's only one other person. I think we're there now.
Okay, brilliant. Thanks, Lou. Right, yeah. So yeah, I mean, the weather's been absolutely atrocious. I think I've probably spent since October, there's probably about a dozen nights where I could actually go out and do some observing or do some imaging. So we're all hoping that things are going to improve a little bit going forward. But yeah, it's not been good. It's not been good for us really. And considering we're in lockdown, this would be a good opportunity for people to get out and do some observing, because it is obviously one interest that we can do solo, and a lot of us do on our own. So we're not going to give anybody COVID. So to begin with, I just thought I might just talk about us in the sun. We are moving. Hard to believe that in our winter we're actually closest to the sun. The Earth gets in its orbit. You all know that the orbit isn't completely circular; it's elliptoid. So at this point, we're at our closest. And then again, well, we've actually passed. It was actually on the 2nd of January. So I'll put a little bit of a blurb up there. So Earth orbit, which is called 1 AU, 1 astronomical unit. So when you hear us talk about AUs, and we only tend to talk about AUs on local distances, because it's only in astronomical terms, it's a very short distance. It's only between 150 million kilometers to 93 million kilometers. Whereas when we talk about things beyond our solar system when we talk about light years, and you obviously know that a light year is the distance that light travels in 1 year. So that's a little bit about that. So that's actually passed. But there's a little image there I thought was quite interesting. It's an image of the sun at perihelion, where we are at the moment. You can see the size difference in the summer. So that's quite interesting. Okay, so I picked a few bits and pieces up of interest. Mars is quite high at the moment and quite easy to spot. It's in the southern sky. One of the features is coming up shortly. I couldn't get an image of it, unfortunately, but on the section here, there's a V, which is quite easily seen normally. And this is just a drawing. It's not a photographic image. But yeah, Mars is still quite full to look at, and through a telescope, you'll see a bit of detail. And if you image, you can see a lot more information. One Facebook page worth looking at is Damien Peach's pages, because some of the planetary images he's done are absolutely superb, and he normally allows anybody to go on and have a look at his images. I'd recommend that. So currently there we are. That's from the 1st of Jan to 31st of Jan, Mars. So we've got Hamill, which is quite a bright star there, and it's just above the moon, so it's quite easy to find. So, and it's quite distinctive. It's like a bright star, but an orangey colour, so not difficult to pick out, but certainly quite visible at the moment. So next item of interest I thought was Mercury. We don't get to see Mercury very often because it's obviously inside our orbit, inside Venus's orbit, very close to the sun, and it's only visible at certain times, just when the sun's either setting or when it's rising. But it reaches its greatest eastern elongation on Sunday the 24th. So if we've got a clear sky, it might be worth taking a look, but obviously you need to be cautious. Wait till the sun actually goes down. Don't look at the sun, whatever you do. It's very dangerous, even when it's at a low in a low position. But it will separate from the sun by up to 18, just over 18.5 degrees. It's a magnitude -4 planet. Will remain above the horizon for at least 2 hours after sunset. So if we do get some clear skies, certainly might try this myself, have a look. Don't often get a chance to look at Mercury. There's quite a nice little picture of it that I picked off the internet. So as I said earlier on, it's the most inner planet. It's quite faint because of the sun's glare. So there's a little bit of blurb there, really reflecting what I've just said. So definitely worth a look if we get some clear skies. Try and be optimistic. Okay, another interesting thing to look at this time of year. I'm going to go over to Stellarium now, because I just want to show what part of the sky we're actually looking at here. Okay, so this is the cluster M35. It's called the Shoe-Buckle cluster. But if you can see there, we've got Orion's belt and Betelgeuse in Orion there. So we're looking sort of almost directly southeast here. So this is, if you're looking at the end of his arm there, coming up to here. So there's the Hades and Aldebaran there. And if you follow that star down here, just above here, we've got M1, which is the Crab Nebula. So that's not an easy thing to see unless you've got a really clear night and a good set of binoculars. If you come down here, this is quite a beautiful cluster. And I'll go back to my image. So yeah, this is a very beautiful cluster. So it's in Gemini. Several hundred stars, of which 120 are brighter than magnitude 13, which is quite visible by the eye. And it's got a regional density of 6.21 per parasec, per parasec. So very pretty, very pretty. We've got some different colour stars in here. So that's one to look out for. So yeah, I've just taken a screenshot there just to show where we are. So some other interesting things which we would really all be looking at this time of year is all the nebulas and clusters and various bits and pieces we've got around Orion. It's a very busy area of the Milky Way, so there's lots of stuff in here. So this is a picture that I took. It's not very good because it was quite a cloudy evening of the Horsehead Nebula, which is in Orion. So this is the third star coming down in the back. If I go back. Let's go back to I'll show you exactly where that is. So yeah, so there's Orion's belt there. I'll swing around. So the star Alnitak there, and you can see as I'm moving a bit closer, that's the Flame Nebula there, and there's the Horsehead Nebula there. So I'm obviously round at an angle, so I've turned the image round so it's facing the other way. But as you can see, it's quite spectacular. This is dust cloud just she's blocking off this nebula at the back here and just happened to create the shape of a horse's head. I should have to stop the share each time to jump between screens. Maybe I don't, maybe it's me. Let's go right off now. That's great. Okay, so yeah, that's quite a nice picture. Something worth if you are doing imaging, it's something which is quite popular. So this one here is the Orion Nebula. Steve took this image, I think just for Christmas. I think very good, but I mean this is actually superb. This is a huge star forming area, which is quite local to us in astronomical terms. This nebulosity and colours he's achieved with his camera is absolutely superb. So this is something I've been trying to image for the since Christmas, just before Christmas, but just haven't had any clear nights to do it. It's really low down in the sky. It's near Sirius, or just a little bit east of Sirius. I'll show you in a minute where it is, but it's quite an interesting object. It's called Thor's helmet because it looks a bit like Thor's helmet. We've got the helmet section here and the wings coming outside. And the interesting thing about this particular nebula, like some other nebulas, and the reason they have such strange shapes is that the central star in this nebula is what's called a Wolf-Rayet star, which is quite a rare star, unusual star, which burns very hot and bright and starts to give off a lot of its material before the end of its life, unlike supernovas where the star at the end of its life will explode and give off all of its materials. This is doing it through its life, so it burns very quickly and has a very short life. So it's quite an interesting object, but I think that's something I'm going to have to image next time I go to Spain because it's just a little bit too low. I'm trying to come through too much atmosphere. I'll just show you where that is. That's the okay. If I zoom out again, just go back to Steve's image, which was the Great Orion Nebula, which is here, just down from Halifax, as you can see. So if you're looking at Orion's Nebula, you see the sword dropping down. This is the middle star, and what appears to be a star in the middle of his sword. But if you look at it through binoculars, you'll see it's fuzzy and a little. It'll appear white, like a little white blob of mist. But with a camera, you'll get the colours. You can see that's just slightly around at a different angle to the image that Steve did for us. So yeah, I'll just show you roughly where Thor's helmet is. So if we come down and find Cirrus, so there's Cirrus, and Thor's helmet is just over here, somewhere about here. So as you can see, there's horizon there. It doesn't get very high. It sort of loops over, then drops back down the side here as the sky rotates around. If I just move it forward, you'll see which direction it's moving in. So I'm just speeding the clock up a bit. So as you can see, that doesn't rise very high in the sky. So it's coming around here, and then it's going to drop behind. And I've got houses here I can put up. So that's really interesting things that the sky as far as I've been able to explain tonight. So is there any questions or not? If not, I'll hand back to Alan. Okay, right, back to you then, Alan. Can't say anything there.
Okay, well, thank you very much indeed for that talk, Martin. I think there's some stunning photographs you've got there, and it's terrific information that we are learning about as well. So thank you very much for giving us a guide to that, and I hope that we get a chance to go outside and do a bit of observing. I always think Mercury is a super one to have a look at. I've seen Mercury less times than I've got fingers, but it's quite an exciting moment when you do see it. You feel like something, if I say it's fairly easy, but you've got to be looking in the right direction at the right time. One of the first time I ever saw it was fortunate that Venus was also around. So I'd got Venus as one marker and I could see the sunset as another. And I knew it had to be somewhere in between. So anyway, thank you very much for that indeed, Martin. I'm now going to pass you over to Jerry, who's going to introduce tonight's speaker. So over to you, Jerry.
Thanks very much, Alan. I remember a few years ago, we had this very special event to mark 400 years of the invention of the telescope. And there was this big thing down at Syon Park. And as a few of us were walking past one of the ornamental fountains there, there was a statue of a certain classical god there. And I said, oh, look, daylight vision of Mercury. Anyway, I am really delighted to be able to welcome Paul Daniels this evening. Paul, when I originally met him, he was chairman or president
Yeah.
of the Guildford Astronomical Society. Now he is president of the Federation of Astronomical Societies. He's moved up a notch or two. The FAS, which was brought into being 1974, is essentially a sort of over-organization for the various astronomical societies around the country. And it has around 200 member groups at the moment. But it's more than that. The idea of the FAS is to provide facilities for societies and information and advice and help for them, which it did in a excellent form just at the weekend, and holding a webinar on doing outreach, taking COVID-19 into account. Paul's also Vice President of the Royal Astronomical Society, which recently celebrated its 200th anniversary. His interests, particularly of the solar system and orbital dynamics, and that's something which will feature heavily in his presentation tonight. I don't know how many of you have had people who've said, oh, did you see the satellites as they went over? When I was in the care home, I got that a lot from the staff, and my response was generally, oh God, not that light pollution stuff again. Well, there's a bit more to it than that, and Paul is going to take us into some of the problems that having literally thousands of these small satellites in orbit around the Earth can produce. So here with the mega constellation threat, please welcome Paul Daniels.
Thank you very much. I have had some warnings from my system this end that my internet connection is a bit slow. So if anything really goes wrong and I drop out at some point, it might be a time for a comfort break and a cup of tea while I reboot my router. But let's see how we get on.
But Paul, sorry to interrupt there, but I should say to everyone, if you want to pose any questions, please do so in the chat facility, and we will go through those at the end of the talk. Right.
Okay. Thank you very much for your talk, Martin. Just as a little poser for you to think about while you're getting bored of hearing my talk, the Earth can sometimes be closer to the Sun than at perihelion, and not necessarily exactly at perihelion. Okay, so I'll just share the screen for my talk, which should be that one. You see that? Thumbs up. Good. Okay, lovely. So the mega constellation threat. So I'm going to talk about, as Jerry said, the potentially thousands, if not hundreds of thousands of satellites that are going to be launched into low Earth orbit. And so I'm going to talk a little bit about what exactly constitutes a mega constellation, and why they threaten astronomy, how they affect our use of and access to space, and some of the legal and potential international tensions that could be raised by mega constellations. So it all started a few years ago, 1957. Well, for my age, it was a few years ago, with Sputnik 1. And there have been 8,000 or so launches since then, with a couple of thousand active satellites at present. Actually, that's more than a couple of thousand now, because of how busy Mr. Musk has been launching the Starlink satellites. Back in the early days, part of the problem was, or part of the thing was, that satellites were very expensive to launch. They were single satellites launched per launch vehicle, one at a time going up there. They were big, they were heavy, 6,000 to 8,000 kilogram satellites, and the typical cost would be $100 to $400 million. So these were big satellites, typically placed out in a geosynchronous orbit, and I'll come to what that is. And over the years, the miniaturization of electronics has meant that satellites have been made smaller and smaller. And also the launchers have now been made reusable. So the cost of launching satellites has brought that cost down to about $20,000 to $100,000 per satellite. In fact, there are the CubeSats, which are about $20,000. Now, more powerful launchers also means that the number that can be launched at the same time has gone up. And just as an example, the Starlink satellites that are being launched are currently being launched 60 at a time. Now, having low costs means that you can launch a lot at the same time. And if you can do it once, you can do it many times. So you have the potential for launching constellations of satellites. And it's probably fair to say that a constellation can be thought of as 100, perhaps 200 satellites working as a concerted system, and a mega constellation might be thousands of satellites. So the border's a little vague to describe, but with mega constellations, we're talking about thousands. So I want to say a little bit first of all about the kind of orbits that satellites occupy. We have first of all here the high Earth orbit, which is out beyond this distance, which is the geosynchronous orbit radius. Now, this is an altitude here given above the Earth's surface, not from the Earth's center. Then we've got the geosynchronous and geostationary orbits. The difference between these is that geosynchronous means that the satellite is at a distance from the Earth where its orbital period around the Earth is the same as the Earth's rotation rate. So the satellite stays above the same longitude on the Earth's surface, provided that the satellite's orbit is perfectly circular. A geostationary orbit is one that is in the plane of the Earth's equator. So that means that it's not moving up or down above the celestial equator, it's projected out onto the sky, and it's not moving either in longitude, so it stays in the same place, which is very good, of course, if you want to point a fixed satellite dish, like a sky dish or something like that, out to it. Those are the stationary orbits. Geosynchronous relax that restriction of the orbit being coplanar with the Earth's equator. And what that means is that the satellite will stay above the same longitude, but move up and down in a straight line above and below the Earth's equator. If the orbit is very slightly elliptical, so that sometimes it gets a little ahead of the Earth's rotation, sometimes slightly behind, instead of seeing a vertical straight line, you'll see an elongated figure of H shape that the satellite describes. But clearly, if you're going to track those satellites, you'd have to have a dish that can move to do the tracking. Medium Earth orbits are much less common. And an example of a medium Earth orbit is this Molniya orbit here. They typically, for a Molniya orbit, they have a 12-hour period, so they go around twice as the Earth rotates once. They have a particular inclination. That means that they don't precess. The orbit doesn't rotate around the Earth's axis over time. And that particular inclination is 63.4 degrees. And what they do is, because the satellite is traveling so slowly around the apogee point on the orbit and fast around the perigee part, it means that you can have a satellite up here spending relatively long period of time out here and able to therefore spend a lot of time concentrating on viewing something on the ground below. And then the orbit but one after that, it can do the same again. So this is the kind of orbit that's typically favored by the military surveillance satellites. So the Americans, for example, can spy on the Russians because the satellite has a fair bit of time up at the extremity here, up at the perigee, at the apogee point. So the most common ones that now are the low Earth orbits or near Earth orbits. LEO is becoming a more common abbreviation than near Earth orbit. And occasionally you also come across VLEO, which is a very low Earth orbit. So really a low Earth orbit counts as something less than 2,000 kilometers altitude. This number here is already out of date because Mr. Musk has launched by now over 800 satellites into orbit as part of his Starlink mega constellation. That's a lot of satellites. 800 is a very large proportion when you think that there were less than 2,000 before he started launching, and only 8,000 that have been launched altogether. So that's a sign of the fact that these are being launched so quickly, and so many of them. So now I want to move on to talk about the mega constellations themselves, and I'm going to just list first of all a set that we know about. We have SpaceX up here at the top, and these are the ones that he plans to launch. Note that the ones that are currently being launched are part of this 11,908 here, with these applied for. I'll come back to that later on. Amazon have now been given the permission to launch theirs. And there are other companies down here that have constellations or mega constellations of their own to launch. Facebook have hinted that they may want to start their own network up as well. But we don't know exactly how many. Some people have rumored 100,000. OneWeb, this is the company that it's a UK company. It declared itself bankrupt. It went into Chapter 11 in the States and was eventually bought out after restructuring, bought out by the British government and Bharti International, which is an Indian company. They had plans to launch 716 satellites before they went bankrupt. And while they were bankrupt, they filed an application to launch nearly 48,000 more. I think the hope was that if they got permission to launch the 48,000, that would make them a rather more attractive purchase to a potential buyer. As it happens at the moment, they haven't been given permission for the 48,000. So even if you don't count Facebook or OneWeb or these lower ones here, Link, you're still talking about 58,000 satellites, and that's just the ones that we know about. We know that the Russians want to launch their own, the Chinese want to launch their own, and the EU is now also talking about having an EU mega constellation as well. So we could be talking about 100,000 or more than 100,000 satellites over the next decade or so. Okay, so this is specifically, this is about, in general, the mega constellations that are going to be launched. We have now, I'm going to talk more about Starlink because it's the one that's most prolific, and much of the arguments that apply to Starlink will apply to all of the others as well. So at the moment, SpaceX, owned by Elon Musk, is launching the first few of 12,000 satellites that he's been given permission to launch. The ones being launched at the moment are part of this batch here of what I've labeled phase 1. And by the time this first phase is finished, the first 4,400, he will have a very good global internet coverage. He's already started to offer internet coverage in the US, and he's now recently, in the last few days, I believe, being given permission to operate ground stations and have antennae and so on, so he can beam down to the UK. There are big benefits to having low Earth satellites providing internet connections. Suppose you wished to send a digital signal from the UK around to New Zealand. You would have to currently do that by bouncing it off one of the geosynchronous satellites, big communication satellites. But the problem with that is you've got the round trip light time out to something that's 35,000 plus kilometers away, and then back down to the Earth again. It may even be that it's necessary for it to travel up to the satellite, bounce across to another communication satellite, and then down to the Earth again, which would almost certainly be the case for New Zealand. The other possibility is to relay it across land, but you've got to go through various repeaters with bits of electronics in the way, and the signal has to pass through optic fiber, which of course has a refractive index of about 1.5-ish, and so you're talking about the speed of light being 2/3 that in air or in a vacuum. So sending the signal around the Earth or bouncing it off a traditional communication satellite is a serious delay, and that's often why, in fact, when you see overseas television broadcasts, there is a delay between the presenter in the studio in the UK asking a question and the reporter with the microphone out somewhere taking a second or two to catch up an answer. That's the delay caused by the communication. Well, with low Earth orbit satellites, you will have the signal from the ground beamed up to a satellite that is perhaps 550 kilometers above the Earth's surface. The Starlink satellites can use lasers to send the signal from satellite to satellite, and then from that satellite back down to the ground again. And that time is much less than the time taken for the signal to go the other two routes. Some people in the States have already reported speeds of about 120 to 150 megabits per second with about 20 to 40 milliseconds of latency. So that's certainly reasonable. How well it will function when there are potentially millions of users and the total bandwidth that a satellite is capable of managing may be swamped. It may be that the overall experience may turn out to be lower than the initial tests. Back to the satellites, what they have also applied to for phase 3 is this is an additional 30,000 satellites, but they haven't yet been given permission for that. Their applications were filed with the US's Federal Communications Commission, who effectively dole out frequency bands that they can use on behalf of the ITU, which is a UN organization. So this initial 12,000 they have permission for. It used to be the case when you were launching a single satellite that you were given a deadline, and I can't remember, I think it was something like 6 years before if you didn't have the satellite in operation within 6 years, then you lost the right to use that particular frequency. And they realized at the FCC that this would be difficult to enforce, would be unreasonable with mega constellations if you're talking about launching thousands of satellites. So what they've done is they've said that phase 1, this early part here, has to be half completed by the 29th of March 2024. If he hasn't half completed it by then they lose the right to use the frequency bands that they've been allocated. At the rate he's going, he will easily manage to have half of that constellation deployed by then. But it's got to be fully completed 3 years later. And phase 2, that's these satellites here, half completed by November 2024, fully completed by November 2027. So you can see that there are a lot of satellites here to be launched, permission already granted. And that means that he already has a foot in the door in legal terms, in legislative terms, and he's already well ahead of the competition. OneWeb have some satellites launched, but because of their period of bankruptcy, they're very much playing catch up. And having been now acquired by new owners who may have different ideas about what OneWeb do, it may be that they never progress up to the mega constellations that they were originally thinking about. I know also, whereas Starlink is mostly going to be aimed at the end user, the OneWeb is mostly going to be aimed at serving the communication providers. So you won't necessarily have your own aerial pointing up at a OneWeb satellite. You'll see that all of these altitudes are relatively low. The early filings for Starlink, some of them were up around the 1,000 to 1,200 kilometer mark, but they realized that excuse me, there were problems with that, and so they've reduced the altitude of the orbits to down below 600 kilometers. a lot of this also because of conversations that they've been having with the astronomical community, pointing out that high altitudes would be more of a problem. Okay, so this taking the list of orbits that have been published for Starlink satellites, this graph shows down along the side here, shows the latitude of an observer on Earth, and up on the vertical scale here it shows the number of satellites per 100 square degrees at the zenith. So this gives you a rough idea of the concentration of satellites in the sky above at different latitudes. Now, because if I just go back to the previous slide, you can see that if you look at the here, you've got 3,000 satellites at 53 degrees, and here you've got another 2,500 at 53 degrees, and then down here for the future ones you have another 7,500 at 53 degrees. 53 degrees, of course, is about the latitude of Manchester or something like that. So that explains why this spike here is going to be more of a problem for us in the UK. So the initial phase 1 and phase 2, this is the first 12,000, are the top of the yellow bars here. And he has no satellites being launched into a higher inclination orbit than 53 degrees until he gets to the phase 3 satellites. Sorry, some of the phase 2s, but not the phase 1s. Wrong way around, phase 1s but not phase 2s. So you can see, for example, that at the end of launching the 12,000 satellites, there will be something like 0.6 of a satellite per 100 square degrees, which doesn't sound like very much. But bear in mind that the square of Pegasus has an area of 207.4 square degrees. So that means that 0.6 of a satellite per 100 square degrees means that you'll have something like 1.2 of a satellite perpetually in the square, the square of Pegasus. The bowl of Ursa Major's dip has got an area of about 44 square degrees. And if you look at the combined quadrangles above and below the belt of Orion, they're about 82 square degrees. So again, you can see that this figure here, 0.6, amounts to one satellite perpetually being within, not the same satellite, but they'll be passing in and out going through that square. And on average, there will always be one satellite in that square of Pegasus. And I'll come back to this graph later on because it gives us a useful handle on how much astrophotography could be affected. So what do the satellites themselves look like? Well, this shows us here the stack of satellites, all flat packed. I don't know whether Elon Musk got advice from IKEA, but you have here 60 satellites stacked up. If you count these little white bars here on the side, there are 30 of them in a row, and there are 2 tiers, 2 stacks. So there are 60 altogether. Once in orbit, the solar panel unfolds, and initially the satellite is launched into a 290-kilometer altitude orbit, and it adopts this open book configuration where the solar panel is parallel to the body of the satellite. The satellites themselves, as you can see, are quite thin in the vertical direction, and about 1 meter wide and ½ a meter in the other direction. And the reason for using this open book configuration, and why do you launch them at 290 kilometers to begin with, is that even at 290 kilometers, the Earth has an appreciable amount of air there to slow satellites down and cause them to re-enter. It's not really until you start to get up to 1,000 kilometers where the air is very, very thin and has a negligible drag on satellites. There is some, but not much. So at 290 kilometers, they get a chance to launch the satellite, test it out, make sure it's working properly, and only then do they start to move it into a higher orbit. And so they have the open book configuration. It orbits edge on so that it presents the least amount of drag. And then if the satellite is faulty, the satellite will then re-enter in a period of perhaps a month or a couple of weeks or so. Depends on exactly how low it is, whether it achieved full orbit, whether they managed to get it to unfurl properly and things like that. Basically, at 290 kilometers, the satellite has got a relatively short lifetime before it re-enters. This other configuration here, what they call the shark fin configuration, is where the solar panel is rotated at right angles to the body of the craft, and the satellite panel then points perpendicularly away from the Earth's surface, with the flat body here being relatively parallel to the Earth's surface. Something that's been added to the later ones is they've added these little visors underneath. You can see here, this is the solar panel array here going upwards. This is the underside of the body of the satellite, and down here these visors, and these are also deployed at the same time that they switch into the shark fin configuration. And I'll come back to what these visors do later on. So when the first Starlinks were launched, the first one launch, I think it was, they used an earlier version of Starlink, slightly lighter. They only use one of the frequency bands. And when they re-enter, some of them already have re-entered, they are only 95% destroyed on re-entry, but what's left is small shards and small bits that come down. The Starlink 1.0 is what's being launched now. It has the extra frequency band, the Ka band, and the materials used mean that it's now 100% destroyed on re-entry. I'll describe what dark sat and visor sat are later. Common to both are the Hall effect thrusters using krypton gas. It's a small cylinder of krypton gas, and the gas is ionized by a spark effectively, and the ions that are created are then ejected at very high velocity from a thruster nozzle. A very, very small amount of material being ejected at very high velocity gives you a small thrust, to the extent that raising the satellites from the 290 kilometer altitude up to 550 kilometers altitude takes 43 days. The underside of the satellite has got these phased array antennae. If I go back to the previous slide, you can see these areas here are the antennae, these patches here. In the early satellites, they were white, and I think they've now coated them black. But these are the antennae. Now, the antennae are not just like an ordinary television aerial or anything like that. They are highly sophisticated antennae, and they can have multiple beams for receiving from and sending to the Earth surface, and they're also very high speed. They use effectively the phasing of the signals to steer the beams. They're the kind of thing the military have been using for years, but these are now being put into a miniaturized form, not just for the antennae on the underside of each craft, but also the antennae used by the user on the ground. And I'll show you that in the next picture. It has a solar panel about 1 by 9 meters and a star tracker system to make sure that the satellites can accurately point. In addition to that, the satellites are getting a feed of the US Department of Defense data to actively adjust their orbits to avoid collisions with debris and other satellites. So that's one of the reasons why they use the krypton gas, but also for raising to higher orbit, keeping position in orbit, and for deorbiting at the end, and I'll come to that later. The satellites, the ones being launched now, have inter-satellite laser communications so that a signal can be ricocheted from satellite to satellite around the globe to then feed from one side of the Earth to the other. What you have to recognize is that the satellites that are at 550 kilometers, for example, have a fairly small footprint on Earth. From there, you can only see about 4% of the Earth below. Whereas the satellites out at geostationary or geosynchronous orbit can see about 40% of the Earth's surface. So that's exactly the reason why, the fact that it's only 4% of the Earth's surface, why you have to have so many of these satellites, because you've got to give, if you want the full coverage, global coverage, you have to cover the Earth's surface with enough satellites, enough 4% with some safety and some overlap to be able to give you the coverage. So that's the disadvantage of having a satellite at 550 kilometers instead of say 1,000 or 1,200. Okay, so this slide here shows what the ground station looks like, and these are now going on sale in the UK as well. His program is known as Better Than Nothing Beta, and in the US, the startup kit that includes the router and the dish is $499, and then it's $99 per month for the broadband. So it's not cheap, but if you live in a remote part of the US, it may be the only broadband you're ever going to get. So it's a 19-inch diameter dish, Dishy McFlatface it's known as, and this rather weird futuristic looking router down here that looks like it's some alien spacecraft that's coming to land. So at the moment, it's got lapses in the service because there isn't the satellite coverage that there eventually will be, but people know that they're buying into something that's imperfect but will improve. So this is what you may see around the UK at some point. They are going on sale in the UK, I think, for £484, and I think 100 and something pounds per month. And again, there are parts of the UK where coverage isn't good, and it's the only way they're going to get broadband. So in filing their application with the FCC, Starlink have to make certain promises that in what they will do, what they will design into their spacecraft. The first one is that they mustn't collide with each other, and SpaceX have said, well, you know, we've designed autonomous collision avoidance into them so that they will be safe. Bearing in mind that a 1 kilometer CubeSat, and the CubeSat, the smallest CubeSats are about 4 inches by 4 inches by 4 inches, traveling at a typical orbital velocity of around 7 or 8 kilometers per second, has something like 6 kilograms worth of TNT energy in its impact with something that's stationary. It could, of course, collide head on, or it might be a catch-up collision so that the relative velocities are quite low. But on average, you may well get a 7 kilometer per second collision. So there's not going to be much left of the CubeSat after that, and probably not much left of whatever it collided with. So you're going to end up with a lot of debris in orbit, and therefore debris is what you really want to avoid. And you can see here a difference in approach between ESA and NASA. ESA refer to greater than 10 centimeters, 1 centimeter, 10 centimeters, 1 millimeter to 1 centimeter, and NASA use bigger than a softball, bigger than a marble, or too small to track. Either way, their estimates are in the same sort of ballpark, or is that soft ballpark, where you can see that even a small particle of 1 millimeter to 1 centimeter, there are hundreds of millions of them already in orbit around the Earth. So you don't want to add to that. If we don't tackle the space debris problem, and there are companies now, startup companies now, that are working hard to devise ways of clearing debris out of Earth orbit, then we're going to have a problem in the future with the viability of satellites, and even the possibility that we won't be able to launch into space, or even if we're moving out beyond low Earth orbit, we won't be able to move through the cloud of debris that's there reliably. Insurance costs might make it unfeasible to launch satellites, for example. The other thing is that they can't explode. You must design them not to explode. Batteries can fail and could potentially could go bang. Electronic components can fail. Capacitors can fail, things like that. And also, of course, if you've got a compressed gas cylinder, that could suffer an impact or could fail. A seal could go or something like that on the cylinder, and you could lose gas and have it jet out of control. So again, you don't want the satellite to have any part of it that can explode in its own right, but also you need to provide extra protection for these components to make sure that they're not impacted by other debris, small particulate debris, or of course natural micrometeoroid impacts. Excuse me, right. The other thing is that SpaceX have to provide the FCC with their plans on how they're going to deorbit the satellites. NASA generally work to a 25-year lifetime on satellites in orbit, and they're now starting to enforce that policy quite strongly within their own ranks. And satellites that are in a 550-kilometer orbit will deorbit within 5 years, solely due to atmospheric drag. Even at 550 kilometers, there is enough atmosphere for 5 years. This is one of the other problems for the OneWeb satellites out at about 1,000 or 1,200 kilometers, where they're proposing to put them, because at that altitude, they won't re-enter within a century or two. It's they're up there effectively permanently, and they're talking about just literally moving them up into a graveyard orbit and not seeking to re-enter them, which is contributing to the space debris. I think they're going to have to force OneWeb to change their minds about that, because there is too much momentum within the space community for satellites now to be considered reasonably just left in a graveyard orbit. So what they will do with the Starlinks is they'll use some of the remaining fuel to lower the perigee. In other words, you've got it's a bit odd to talk about perigee on a very circular orbit, but lower the perigee to about 300 kilometers or less, but keep the apogee at the same altitude of 550 kilometers or whatever the operational orbit was. This will take some time, again, because those krypton gas thrusters are very low thrust. It will leave it with enough fuel, and they must make sure they retain enough fuel, so that as the satellite then starts to deorbit, it will cross, its orbit will cross that of satellites in lower orbits. So you'll see the satellite orbit, for example, cross the orbit of the ISS and the Hubble Space Telescope, and all of the Starlink satellites that are in lower orbits. So they've got to retain some fuel to allow them to maneuver and to avoid other things. They will also change so that whereas the satellite has been optimized for service in its service orbit, they will rotate the satellite so that the cross-sectional area in the direction of orbit is maximized, so that you increase the effect of atmospheric drag. You actually encourage the re-entry of the satellite. Spin down reaction wheels, drain batteries, power down, all those sorts of things. And within a fairly short space of time, a few weeks or a few months, the satellite will re-enter and be destroyed. Of course, this doesn't address entirely what happens if the satellite has died. Not so much worried about whether it will re-enter. I'm sure it will. From 550 kilometers, 5 years, it will re-enter. But if you can't command the satellite anymore, and if you can't therefore use the fuel to avoid other satellites, you have effectively a rogue satellite slowly spiraling inwards. Everything else will have to maneuver out of its way. Now consider the number of satellites. If we're talking about, let's assume that for the moment that they do get permission to launch all 42,000 satellites. With a lifetime for each satellite of 5 to 7 years, and that's mostly determined by the amount of fuel on board each satellite, and also how much of that fuel they have to use to keep station in orbit. They use the fuel just to tweak the orbit slightly to make sure it stays in place. And that depends also on solar activity. As we come up to solar maximum in about 4 years' time, the atmosphere on Earth swells up very slightly during high solar activity, and therefore the amount of drag is marginally higher. So over the next few years, you might find there's only a 5-year lifetime for these satellites because they need to use more fuel to stay on station. 42,000 satellites divided by 5 or 7 years means that you have to replace between 500 and 700 of these satellites each month, because there are 500 to 700 on their way down to re-entry and 500 to 700 launched to go up to replace them, which means you've got pollution from the launch vehicles, pollution from the re-entry. All of those rare earth metals in those satellites are now being vaporized and scattered into the atmosphere. It means also that even if you assume that those satellites are only going to be visible for half of the time in their transition from orbit down to re-entry or vice versa, from launch up to orbit, it means that you're going to have something like 600 satellites visible around the globe somewhere in the night sky. Not necessarily 600 over your head, but some that will always be bright enough for naked eye visibility. SpaceX have said that what they will do is they will try to orient the solar panels for minimum interference with the ground observations. In particular, they have a problem with satellites that are near the horizon in the direction of sunset or sunrise, because you get glinting off the panels. It doesn't affect the professionals as much, but it might affect people wanting to do, some amateurs wanting to observe near the horizon. And it may also affect some telescopes that observe in that region, trying to discover, for example, comets that are close to the sun, or other near Earth objects, potential near Earth objects that could be coming out from near the sun in that direction in the sky. So with 600 satellites re-entering the Earth's atmosphere each month, that means that 20 per day, somewhere around the Earth, there will be 20 satellites per day re-entering. So we've got the potential for a chain reaction. This is the Kessler syndrome. If you remember the film with George Clooney and Sandra Bullock, we have the potential here for a collision between satellites. If you have one that goes rogue, it stops working properly, you could get a collision, lots of debris, and the debris can cause more debris, and so on and so on. One of the arguments against this is if you have a low Earth orbit satellite, it is sufficiently low that atmospheric drag will cause the debris to re-enter. I've had a conversation with Professor Hugh Lewis at Southampton University, who specializes in space debris. He feels that it's not going to be a significant problem because they're at low Earth orbit. My feeling, however, is that if there is a collision, there could be a spike in debris, and that spike will eventually decline because the debris will re-enter. But it may be that that spike, especially if you get a collision causing another impact somewhere, you could have that spike persevere for a long period of time, longer than it takes for the original collision's debris to re-enter, even if it never quite builds up to being the full Kessler syndrome. In particular, it might make it very difficult to launch satellites. If you've got a lot of satellites up there, you've got lots of debris up there, it means that finding a launch window, already a difficult thing, partly because of weather and partly because of other satellites in orbit, this will make it very, very difficult to find a large enough, safe enough launch window to launch things up to the ISS, for example, or to launch craft that are going out beyond. If you're sending a spacecraft out to go and, I don't know, do a flyby of Jupiter or something like that, you've got to get it out through this shell of satellites in low Earth orbit. And I wouldn't want to be on the ISS if there is a hailstorm of debris flying around at 7 kilometers per second. It would make the ISS a very unsafe place to be, and all of the science and all the research that will be lost because of that. So moving on now fairly quickly, I'm about halfway through, so I'm going to need to speed up. We've got the radio bands here that are allocated to various uses. Starlink has these two blue down pointing arrows allocated for downlinks and this green one for uplink. And they have said that they will reserve a 250 megahertz gap between this downlink and this radio astronomy reserve band here. So these pink bands and some others are bands that are reserved by the FCC and by the ITU in fact, for radio astronomy. The difficulty with radio astronomy is, of course, that you may be looking for the emissions from a specific molecular species, a water molecule, hydroxyl radical, cyanide molecule, or something like that, and they will emit at a certain set of characteristic frequencies. But of course, if you're looking at these in a distant galaxy that's redshifted, then it could be that the emission lines that are from water, say, that are coming at a particular frequency will arrive here shifted into a part of the band that isn't protected. So radio astronomy already has to work with the problem that sometimes it needs to make observations in parts of the band that aren't protected. Starlink is going to add to this problem, not just because it means that, of course, it's another portion of the band that's taken up, but also because there are going to be so many of these satellites in orbit, and avoiding them is going to be very difficult. So we've got things like the square kilometer array in South Africa. And around that, there is a radio quiet zone. So you're not allowed to take your mobile phone within a certain distance or have other types of transmitter. And there are other radio observatories that have similar radio quiet zones around them. The problem is that these satellites, if they pass through the beam and they beam their signal down to the square kilometer array, they will burn out the radio receivers very quickly attached to the square kilometer array. So Starlink have said that what they will do for the major radio quiet zones, they will steer their beams away from the radio quiet zones so that the beams don't point directly at the square kilometer array. Anyone who knows about radio astronomy, of course, knows that you get side lobes to your beam and you get side bands to the frequencies that you use. So it's not quite as surgical, perhaps, as SpaceX would like us to believe. The other problem you have is that even if you didn't transmit anything from these satellites, the larger installations, such as, again, the Square Kilometre Array, Green Belt, and so on, they are sensitive enough, and their sensors and their receivers are so sensitive that they can detect the electronic noise of the electronics within the satellite alone, regardless of whether it's actually intentionally broadcasting or not. So in some ways, the radio astronomers have a harder problem to mitigate against the problems from Starlink and other mega constellation satellites than the optical astronomers do. So moving on to talk a little bit about the optical side now, the geometry of visibility. At the top here, we've got some satellites in 1,000 kilometer altitude orbit. This is the curvature of the Earth. The whole thing is to scale, except, of course, for the observatory. With an observatory that size, you'd have clouds in the top of the dome. And we have the sun here at 15 degrees below the horizon. So what you can see is that the shadow cast by the sunlight is going to be below this purple line. It's going to be over here. This will all be in shadow. So what you see here, if you consider 60 degrees away from the zenith, you will have most of the satellites within that cone being visible because they're all still illuminated by sunlight. The reason why the 30 degrees is that that's a typical limit that professional astronomers use. Below that limit, you have problems with absorption by the atmosphere. And certainly down here, you're going to have satellites that may glint. So this may be more of a problem for amateurs who want to observe below 30 degrees, but the professionals less so. Here, all of these satellites will be visible. So this is the 1,000 kilometers that I talked about for OneWeb, and I drew this diagram up when Starlink, when SpaceX was still looking at this sort of altitude for some of the Starlink satellites. Now, if you come to the lower diagram, you can see that the sun is now 30 degrees below the horizon, and now you can see that only some of the satellites are illuminated. This part of the cone above your head, this part of it is now in shadow, and you will not see those satellites. Maybe if you had really sensitive sensors, you might see them as very, very, very faint. There might be enough atmospheric glow or enough perhaps light from the moon or something like that illuminating that they will be visible at a much lower magnitude. So the angle of the sun below the horizon is important. And also the angle between the sun, the satellite, and the observer is important. So just moving on to a diagram that's, I'm sure, is teaching granny to suck eggs, as they say, for most of you. This shows an observer here with the green ellipse being his ground plane, the North Pole star up here, and this is done for the numbers on here are for the latitude of Birmingham, 52.5 degrees north. So you can see here that when the sun is up near the northern tropic here, you've got the sun only 14.1 degrees below the northern horizon in midsummer. And down here, 60.9 degrees below the horizon in midwinter. So clearly this problem of the illumination of the satellites is very much a seasonal one, because it all depends on how far the sun spends below the horizon and how far it goes below the horizon, how much time it spends below the horizon. So if I come on to this one here, this graph was designed to show the percentage of satellites illuminated versus the elevation of the sun. So down here at the bottom, I've got the angle of the sun below the horizon, and up here, what percentage of satellites are illuminated. So the white line here is for satellites in a 290 kilometer orbit. This is the preliminary test out orbit. So you can see that if you wanted to get down to the point where 50% of the satellites are in the shade, 50%, you'd have to have the sun only about 16 or 17 degrees below the horizon. Whereas if you have satellites up at 550 kilometers, 50%, the sun has got to be below 24 degrees, which it never will be in the summertime. So in the summertime, you will get almost all of the satellites, so you'll get many of the satellites visible for much longer into the nighttime. So in the summertime, the problem will be greater than in the wintertime. And also you can see from this, the red line, why the high altitude satellites that are being proposed by OneWeb will be more of a problem, because you've got to have the sun at a very much lower angle for them to be invisible. In fact, some of these will be visible all of the time, even in the middle of winter. So if that's the sort of the geometry of the problem, and there are people busy modeling the brightness of the satellites, trying to work out how we can predict how bright they will be. And that's important if you want to try and work out how to orient the satellites to reduce the amount of light that's scattered down to the ground. Problem is difficult. Satellites are multifaceted and they have a range of albedos, light spots, dark spots underneath. Depends on the cross section, on the sun satellite observer angle. And for some of the early ones that were launched, the estimate was they were between about 4.2 and 5.9 magnitudes for the ones at 550 kilometers. In practice, they are a little bit fainter than that, but they are right at the threshold of naked eye brightness. In the early stages, when they have just been launched and they are still rising up to their station orbit, they are brighter than that, and they have been seen at between magnitude 1 and magnitude 3. And again, also glinting off the solar panels near dawn and dusk when you get glancing sunlight reflection off the solar panels. They tried to coat the underside of the satellites with a dark coating all over the underside of the satellite. It only reduced the brightness by about 0.8 of a magnitude, but they also got problems with the satellite overheating because the dark coating was absorbing sunlight and was basically running at a higher temperature, and that reduces the lifetime of the satellite, increases the likelihood of failure. So that was the purpose for adding these visors that I showed you earlier. The idea is that they will have these visors at perpendicular to the body of the satellite, shading the underside of the satellite from sunlight. So this is a kind of parasol, if you like, to make the underside less bright. Also, they use something called a magneto-torquer to constantly realign the satellites to reduce downward reflections. Now, if they had to use the krypton gas fuel to rotate the satellite continuously, that would use too much fuel, and the satellite lifetime would be even shorter than the 5 to 7 years it currently is. So a magneto-torquer is effectively 3 big coils at right angles to each other, so there's an X, Y, Z axis, if you like, and they pass an electric current through the coils selectively, and the magnetic field generated by those coils then reacts against the Earth's magnetic field to produce a torque on the spacecraft. So it's a very subtle effect, a very novel effect, but it's enough of a torque, enough of a twisting force to mean that you can keep the satellites oriented in orbit without having to use fuel. So this table here is similar to the table I had in my article in the FAS newsletter, for those of you who have read it. We've got here observations made of the satellites at different elevations here, 0 to 90 degrees. And then we've got 3 orbital altitudes under consideration here. So this is the distance of the satellite. If you look at a satellite at 40 degrees, at 550 kilometers altitude, it will be 812 kilometers away because you're looking at it at an oblique angle. How big will it be? Well, same thing here. It would be about 2.3 seconds of arc across. And then how fast is it traveling across the sky? I give 2 numbers here, 23.6 and 32.1. One of those is the angular velocity if it's traveling along a meridional line, if you like, traveling from the horizon directly up and over the zenith. That would be the angular velocity in that direction. The other velocity is the one that you would have if the satellite is to your south and is at sort of the apex of its orbit before it starts to go southwards again. That's where it's traveling perpendicular to the line of meridian. So that gives you an idea of the range of angular velocities for the satellites. What you can then do is you can then use this this formula here, where this is the number of satellites that you would expect to see pass through your field of view. This is the density of satellites in the sky, and you can get this, or an estimate of this, from my graph earlier. This is the field of view of your telescope, the time you have your exposure, and then here, this angle is the angular velocity in arc minutes per second from the table up here. So if you multiply these together, you can get an idea of how many satellites are likely to pass through your field of view in the given time of your exposure. So let's look at this here we have, I just give some typical examples here. If you assume that the density of satellites is about 1/4 of a satellite per 100 degrees, an exposure of 10 minutes, which is not unreasonable for many amateurs to do a 10-minute exposure. And if you go up to the table here, you can see that 30 arc minutes per second is not too far out as a typical figure to use. If you have a pair of 10 by 50 binoculars with an 8-degree field of view, and you're gazing through those binoculars at the same point in the sky for 10 minutes, you're likely to see 6 satellites cross through your field of view. A typical telescope with a 1-degree field of view, you're likely to see 3 satellites pass through in every 4 minutes. Something like, sorry, no, rephrase that. 3/4 of a satellite in 10 minutes. So that would be, yeah, okay, I won't scale it up. 3/4 of a satellite in 10 minutes. The large format camera in the Hale Mount Palomar telescope has a field of view of 0.16 of a square degree, and so you would see 0.12 a satellite. Now that doesn't sound a lot, but of course, very often these large professional telescopes are doing exposures much longer than 10 minutes. The big problem occurs when you have some of the wide field of view telescopes, the camera telescopes, if you like, and in particular, the Vera Rubin telescope is going to be very significantly affected, and it's not even finished yet. Pan-STARRS, 7-degree field of view, in a 10-minute exposure would have about 5 satellites pass through the beam. The Vera Rubin telescope, if it observed for 10 minutes, it would have 7 go through its field of view. Now, for the Vera Rubin telescope, it typically doesn't expose for that long. It has this immense camera, huge camera, very, very sensitive. Most of the exposures are 15 seconds, or going to be 15 seconds. And so they will take a 15-second exposure, looking at one particular point in the sky, followed by a second exposure at the same point in the sky, also 15 seconds. And then they'll move on to take a picture of another part of the sky. And I think the aim is to do a complete survey of the sky that they can over every 3 days or so. The whole point of the Vera Rubin telescope is that you can take pictures and you can compare one set of images of the sky with the set of images from only a few days earlier. You've got this continuous trail of what the sky looks like for analysis. And if you've got all of these satellites passing across its field of view, it's going to be very difficult to determine what's fixed, what's moving, and so on. Some things can be removed and some not. I'm just going to switch over here now to this particular address, and it's one that you can all get to. It's accessible publicly from the internet. So I'm just going to stop my screen share, switch over to my other one. No, this is the right one. Okay, can you all see that? Okay, good. What we see here is, this is just something I knocked up. It runs in your browser, uses JavaScript, and uses a library package called 3.js, which is effectively a wrapper for WebGL programming. What we have here is the Earth. To switch to it. And I can use the keys given in the key on the side here to zoom in. So we're a bit closer now. And over here, I can turn on, these are the satellites in phases 1 and 2. So you can see here, this is 12,000 satellites orbiting around the Earth. And you can see what I mean about the 53-degree point. where here above the UK, we have satellites appear to be in a concentration. That's simply because the satellites come up in an orbit, reach their apex here before they start to go south. And because they're traveling sort of constant velocity around the Earth, but the rate of change of latitude slows down as you get to the top. And then, of course, at the very top, they're not changing latitude, and then they start to head southward. So you get a lot of them at these sort of altitudes. And if I were to add on the other 30,000 satellites, this is what you have. And you can see here that there is very clearly the outer satellites from phase 1 and 2. And here in yellow are the 30,000 inward. And if I were to move in, you can see also that we've got some of the high inclination satellites here going over the top. But very clearly here, those who live in the southern UK are going to see a higher concentration of satellites than further south, for example. The reason why 53 degrees was chosen is it gives good coverage in the US, which is one of his main concerns. Okay, let's just stop that. Go back to my slides. Okay, so as I say, you can actually go and look at that yourself. I've actually put I've done a PDF of tonight's presentation and have sent that to Alan so that you can have a complete PDF. And so if you need to see the link, it'll be available there. Okay, so what's affected? The fast transients, this is the professionals, fast transient observations. If you're looking for things changing in the night sky, basically, they're going to be affected by having all of these satellites. We've got wide field all sky surveys that I talked about with the Vera Rubin and so on. And if you're looking also for objects like near-Earth asteroids and comets, you're looking basically for moving dots of light, and Starlink is going to make you going to provide those in abundance, making it very difficult to actually see near-Earth asteroids and comets. And in particular, also, of course, it impacts on those who are specifically looking for near-Earth asteroids that are a collision risk. So this is a simulation of what the Vera Rubin telescope will see. As I say, it hasn't yet had first light, still in construction. It's a billion-dollar telescope that is from day one is going to be working at well below its capacity because of Starlink. This streak across is the streak that could be caused by a satellite. This is a saturated streak, meaning that it's not just brightness that you might be able to compensate for in the profile and remove. You've actually saturated the sensor at this point so that you have no way of recovering what other information may have been underneath it. These lines alongside are artifacts caused by this very bright streak. They're echoes, if you like, across the sensor. They potentially could be removed because they don't saturate the sensor. The other problem you have is that if you get a satellite pass through the field of view, the CCD sensors can retain a ghost of the previous image, which means that if you're taking two pictures of the same part of the sky, you're going to get the satellite the first time it passed by, and then you're going to have perhaps the ghost of it in the second picture. So you can't even necessarily remove it completely then. It's a serious problem. Not only do you get these ghost images, but you can also get reflections inside the telescope that can cause ghosting effects as well. It's been estimated that from day one, Vera Rubin will be only about 50% effective because of Starlink. This shows you the Hubble Space Telescope. This is a curvature of the Earth to scale. This ribbon here is the typical ranges of orbits being used for at least the phase 1 and 2 of Starlink. And this green box here is a highlight showing you the orbits, the coloured lines of the different orbit levels. The HST, the Hubble Space Telescope, orbits roughly between the range of altitudes given by these dotted lines here. So you do have some potential for collision or debris impacts. If a Starlink happened to collide at that altitude, you're going to have debris at the Hubble Space Telescope's altitude. But the other problem is, if you imagine the satellite here within the green box, if you're making observations upwards away from the Earth, you're looking through a very thin layer of the satellites, and therefore you may get the occasional one pass through your field of view. However, if you're trying to take observations from the Hubble Space Telescope looking in this direction, you're going to be looking through a lot of satellites in this part of the orbit or this part of the orbit. And already we're seeing reports of Hubble Space Telescope images being spoiled. One of the big advantages of a space-based telescope is you can do very, very long exposures. But you can't do that if you're going to have them with satellites passing through their field of view all the time. There are two other satellites, Cheops and WISE. I won't go into them in detail, but they also could have their observations affected by this mega constellation. So they don't have to be illuminated. Infrared, you could have a satellite, if you're observing in the infrared, a satellite illuminated, moving into the shadow, but still glowing because it's being warmed by sunlight. So I discussed these issues earlier on. You've got in amateur astronomy, generally a smaller field of view than the big camera telescopes. Also, amateurs tend to use CMOS sensors, which are less likely to be affected. It tends to be the amateurs that have the 1,000-pound cameras that they want to cool with dry ice and things like that tend to use CCD. But your average DSLR will use a CMOS sensor, so they are not subject to trails in quite the same way. So I think the amateur community will be affected, but it depends very much on where you're observing, what part of the sky you're observing, and what you're using to observe with. And there probably will be software apps available so that you can predict what interference you're going to get and just avoid observing certain parts of the sky at certain times. And there may even be the potential for linking that to, say, a hardware shutter, so that you can effectively cut off the satellite as it passes over, and then open the shutter and carry on with your exposure. So there's room there for a niche market for somebody who can make shutters that don't shake, things like that. And also for those who do radio amateur astronomy, beam steering is not going to be very much use, because I doubt if many of you got a radio quiet zone around your back garden, if you have your own radio antennae, and I can't see SpaceX taking small installations into account with their beam steering. So the public point of view, the satellites will be visible as they're rising to their stationary or to their on-station orbit, and as they're coming in for re-entry, towards re-entry. So it'll be something of a spectacle there. The newspapers, particularly the red tops and the local newspapers, have started out by talking about satellites and Starlink satellites as this amazing spectacle to see in the sky. They thought it was rather fun, a bit like a fireworks show. Many of the more serious newspapers are now starting to appreciate the damage this is going to do to our view of the night sky, and in particular to the risk of the debris in orbit around the Earth. Even if you can mitigate the brightness in orbit on station to where they're below naked eye visibility, the public will still see them. And it's a shame if it puts people off astronomy, the fact that we have at the moment a relatively pristine sky and that you can take long exposures is an amazing thing. But people can be put off astronomy if they find that they can't do astrophotography, for example. So I'm in the last 4 slides now. There are always 2 sides to the story. Clearly, there are a lot of people on Earth that don't have internet at all or have very poor internet. And so you have the issues of the demand for internet versus what they might see as a group of elitist astronomers who want to maintain clear skies. Well, they might say, well, tough, you know, we want the internet. It's good for our kids, it's good for our businesses, and so on and so on. So I gave a talk last night, and my throat's starting to give out. So what treaties, what laws are there in place to limit the launch of these mega constellations? Well, none. The Outer Space Treaty of 1967 was initially set up to prohibit nuclear weapons in space. And they said basically that you cannot own space, you cannot own the moon or any other celestial body. No asteroids, no comets cannot be owned. Just because you've sent a spacecraft to the moon, landed on it, doesn't mean to say that you own the moon. And there were various other criteria that came, various other things that came with the Outer Space Treaty, including that it would be carried out for the benefit of all mankind, and if one nation's bound to assist other astronauts that may be in distress, and so on. But one of the other things that came with it is that if any damage is caused, that the nations that launch are responsible for any damage caused by a spacecraft launched from their territory. Now, that might therefore be an issue if you do start to get collisions occur, because if a Starlink satellite, for example, fails and then collides with a weather satellite or something like that, then that means that SpaceX could be held liable for the cost of replacing that weather satellite. And if you can then show that a shower of debris has caused failure of several of the satellites, it starts to make the risk look rather expensive. The Moon Treaty was an attempt by the United Nations to say that all celestial bodies would remain under the jurisdiction of the United Nations. And I think also by extension, maybe, that the United Nations would be responsible for a sort of space traffic control to make sure that everyone played fairly, everyone got an equal share, an equal chance to use space. But that's been widely ignored. There were very few signatories to it. And whereas with the Outer Space Treaty, the US, the UK, Russia, China, and several others all signed up for it, no such response for the Moon Treaty. Now, in 2015, Obama signed an act effectively saying that US companies could own and sell resources extracted from the moon, the asteroids and other bodies, so that if you launch a craft off to an asteroid, then with perhaps the intention of mining iron or platinum or something like that from it, then basically the US companies are allowed to own what they bring back. That's really not in the spirit of the Outer Space Treaty, but well, at that time it wasn't really an option anyway to go mining, and it's really a policy put in place for the future. 6th of April last year, Donald Trump signed an executive order saying that private companies could claim and recover resources in space. But what's rather chilling is that part of the quote that comes from his executive order is, the United States does not view outer space as a global commons. In other words, they don't regard outer space as being shared and owned equally by everyone. He's very much gone for, if we get there first, if we get our foot in the door, if we make that space grab, then it's ours. We can use that. You can't challenge it. And that's a serious problem. Now, there are legal challenges to this. One of them is on environmental grounds, and also potentially the grounds that the FCC should have updated their policy on what they allow for launching on a regular basis. They haven't done that in 30 years, and so they've actually broken the law in not updating their policies. So maybe there's some challenges could be made against the FCC for allowing Starlink, SpaceX to launch the Starlink satellites. And it may well be the reason why that other 30,000 hasn't been approved yet, or why the 48,000 that OneWeb wanted to launch hasn't been approved yet. So last two slides. SpaceX are already well underway. They're getting military contracts left, right, and centre for the use of Starlink, and they've already got the US Air Force with developing its advanced battle management system, and Starlink will feature in that. Because for one reason is that SpaceX, the Starlink satellites will allow better communication in polar regions than they currently have. And Donald Trump, of course, then set up the US Space Force, designed to protect American interests in space. And it fits in with the US military plans to have a US Space Force as a fourth force. And I just want to very quickly switch to show this Vision for 2020 document. So I'll be very quick over this now. So you can see here this Vision for 2020 document. This document was written by the United States Space Command, as it was called then. It wasn't part of the armed forces then, in 1979. And the document is highly coloured. You can see here it's signed by several generals and commanders in chief and so on. They have this, remember this is the days of Star Wars, the film, and they have this Star Wars-like lettering down here. You half expect to see a large spacecraft coming from above somewhere. And you can see here that the document looks more like something that's come from the Public Relations Office of Ming the Merciless than from an American military organization. But some of the phrases here: full spectrum dominance, going for information superiority depending upon space. And they recognize here space superiority is essential. Space systems will be targets. So effectively what they're saying is we have to have enough space resources up there to counter any threat against our satellites that are up there. And then they have control of space. So just some of these phrases jump out from the headlines. And at the end, they have this, what looks like this sort of a laser cannon here. If you can imagine taking the laser cannon away and putting something like the Death Star there, this is rather reminiscent of science fiction. It's all very worrying that there is this kind of militaristic view of space seen from the US. It is going to be a very valuable commercial resource, not just because potentially of minerals and things like that, but also because space, people are moving, the world is moving out to space. We're going to have bases on the moon, bases on Mars, and so on. And so space is a valuable commercial resource, and the Americans are clearly intent as a policy of having a strong foothold there. So final slide. The US clearly wants to dominate the use of space. International treaties are the only way you might be able to rein in some of their ambitions. And similarly, of course, put constraints on what the Russians and the Chinese and the EU and others will do. There is currently no regulation to stop these sorts of things happening. There needs to be, because the regulations were put in place in 1967, the Open Space Act was put in place in the days when you launch satellites one at a time, not 60 at a time. And by the way, when Elon Musk gets his Starship going, it will be capable of launching 400 at a time. not 60 at a time. You already have problems maybe with certain repressive regimes not wanting uncensored internet available from satellites in the sky. And I actually read today that the Russian government is planning to fine any of the Russian citizens or Russian businesses that make use of Starlink. That's because they've gone to a great deal of trouble to put a digital barrier around their country so that they can not only control what their citizens see and read about on their national internet, if you like, but also, of course, they can monitor their citizens. And if you now have a way of the citizens getting their internet from the sky above, the global internet from the sky above, then Russia isn't going to like that. And you could imagine that countries like Iran might not like that, China might not like that. So that raises a lot of tensions with those countries. What if they decide that they're going to take pot shots at American satellites to reduce the ones that fly over their country and cause them a problem? You may have, as a final parting shot, you may also have the situation where if the US government has some control over what SpaceX do and how they operate their network of satellites, you could potentially have it such that if the US seriously falls out with a country, that they tell SpaceX to stop broadcasting or stop providing internet services to a particular country. Effectively, you turn off the beams as you fly over Iran. And that's effectively allowing the United States to impose digital sanctions on other countries. So I think there's a lot of need for regulation here. A lot of it's still going through. I know that there are already things going through United Nations because of mega constellations and the new problems and the new tensions that they pose. Thank you very much.
Thank you very, very much, Paul. It's been quite something. And shows really that your subtitle for this presentation might have just been a large can of worms.
Yes.
There is so much that
You've frozen, Jerry.
I know Jerry has a bit of a problem sometimes with the internet link there. We'll just give him a moment in case he comes back. While we've got a slight pause there, I'm sure he was in the process of thanking you. Do we have any questions from people? If you'd like to send them in via the chat button, I'm sure we could have them. Okay, we've got a message here from Neil. Are the British government buying OneWeb? I read that it's rumoured that it was bought on. Disappeared before I got there.
Yes, I've seen this before. The thing is, the government clearly this you have to think about this in the context of Brexit. I'm sorry to use the B word, but of course one of the casualties of Brexit was Britain's participation, the UK participation in the Galileo EU project. Suddenly, because we were no longer going to be part of the EU, we were no longer considered to be sufficiently security cleared for what is an EU project, not a European Space Agency project. So, of course, Theresa May initially said, "Oh, well, we'll just build our own from scratch," and that proved to be rather expensive when people worked out the figures. And of course, when OneWeb became bankrupt and were looking for a buyer, you have a company planning to put up a mega constellation going begging. So you got the initial idea was that, well, maybe you can use OneWeb and put GPS equipment on board. In fact, that means you've got to redesign the satellite significantly if you're going to do that. But that didn't stop this government from making an investment in OneWeb. I think it's going to be a white elephant investment in practice. I think by the time OneWeb really get themselves on the move, SpaceX will have entirely dominated the kind of market. The fact that they are already offering internet services in the US and the UK means that by the time OneWeb have got enough satellites up there, SpaceX will have already got fair dominance of that kind of broadband. The thing too, of course, Elon Musk is launching these on his own launchers, whereas OneWeb are launching theirs on Russian rockets. And it comes to a rather odd irony that OneWeb are going to be launching their mega constellation satellites on Russian rockets at the same time as the Russian government is saying we don't want any of our Russian citizens to pick up the internet from these satellites. So I think yes, it is true, and certainly when Boris Johnson became Prime Minister, he clearly had. You've only got to think about the kind of rhetoric he's been using about Brexit. He clearly wants to blow his trumpet, if you like, on saying we've bought the company that can get these satellites up. I think it was a political move rather than a financially prudent move.
Yes, yes, most definitely. I mean, the daft thing about Galileo is that the major satellites were being built in the UK, in fact, by Airbus in Stevenage, just up the road from me, and then we're being told, well, no, you can't use them because you're not part of the EU. I mean, suppose other countries currently in the EU decided to leave and they were told, well, you can't use it either. Are each of them going to put up their own GPS system? I mean, it's such a ridiculous situation to even contemplate.
Yes.
But but here we are. You know, it's not just Elon Musk, as you mentioned, Amazon and others. You know, how many of these broadband providing services are necessary? And they're all competing with each other, all well,
they won't talk to each other, and so yeah, there's going to be complete duplication of effort. I think I think it's crazy. I think it's crazy. They're really the regulations and the international treaties should all have been put in place 10 years ago, when it was quite clear that satellite costs were going to come down.
Yes, and that such a situation as this was possible, then you shouldn't wait for it to happen and then try and dig yourself out of the hole. You should put something over where the hole's going to be dug to make sure you can't dig in the first place.
One of the problems with the FCC is that they have in the States the National Environment Protection Act, NEPA.
Yes.
And NEPA is a requirement for almost all government agencies in the US. Basically, if you're going to build a road or you're going to build an airport or something like that, then you have to do a risk assessment, an environmental impact assessment that can easily add 3 or 4 years to a project and significantly increase its cost to make sure that people aren't going to be affected, there isn't going to be undue pollution and so on. If the FCC have an exception to this, they were granted an exception because they said, well, we're only launching satellites up there, we're only allocating radio frequencies, everything that's going on is going on up there, it doesn't have an impact on the Earth environment. So the FCC were never required to require environmental impact assessments from people wishing to launch satellites. And that's now being challenged because it's being made clear that with mega constellations, you have not only potential pollution because of the number going up and the number coming back and re-entering and so on, but you've also got the potential pollution of the night sky. And so there are some challenges. There are 2 or 3 senators in the States that are challenging the FCC not being subject to NEPA, but it may be impossible to make that retrospective. if they can get it through, it might mean that SpaceX will have to do an environmental impact assessment for the other 30,000 or for the 48,000 that OneWeb want to launch. But of course, that doesn't prevent other countries from launching because they won't be subject to NEPA.
Another question, didn't Elon Musk himself think about what this is going to do to the night sky? And
He did. In fact, he actually said at one point in one of the interviews, he said there will be zero impact on astronomy. And if it is greater than zero, we will mitigate that so that it is zero. It's a very strong, very bold statement. And of course, astronomers are going to work very hard to hold him to that. The thing is, you see, if you've got satellites that are at 7th or 8th magnitude, that's still an impact to professional astronomers in particular. Okay, the public won't see them when they're actually in operation, but 7th or 8th magnitude objects passing through the field of view of a telescope that's looking at objects of 20th magnitude or something like that, that's a bright object. So it's not really a mitigation.
All right. Alan has asked, what's the carbon footprint of launching all the mega constellations in energy terms?
I have to say, I don't know. In terms of carbon, I know that, and maybe you know more about this, Jerry, than I do, but I'm pretty sure that the Falcon 9s use methane as their fuel. Is that right? So if you're burning methane to launch them, then maybe that's a concern, because the methane will produce carbon dioxide on combustion.
Oh, also 60 at a time, 30,000, 500 launches.
Yes,
That's
600 or 700 going up each month is a lot of pollution. Yeah. So the answer is I really don't know, but I suspect it's not insignificant.
Someone else asked, what might Elon be thinking about next in relation to this field? Well, we have to wait and see.
I don't know. I mean, Elon Musk started out way back in the early days of the internet. He set up a company called X, which was designed to facilitate purchases on the internet, and eventually X merged with another company and became known as PayPal. And that's where Musk made a lot of his initial money as one of the founders of PayPal. He invested that money to get Tesla going. He made a lot of money from Tesla, and he's invested that money to get SpaceX going. And he says that the reason why he wants to make money from Starlink is because he wants to fund humans traveling to Mars and setting up Mars colonies. It's interesting to note that Musk is on public record as saying that he doesn't believe that when humans live on Mars, that they will be bound by rules made on Earth. Effectively, he's looking to set up a Musk colony bound by his rules or the rules that the early colonists developed.
Okay, well, a couple of years ago, to mark the 50th anniversary of the Outer Space Treaty at the British Interplanetary Society, and this was one of the things that we discussed, whether groups living on the Mars or on free-floating space habitats, what legal framework would they be bound by? And de facto, it'll be whatever they want, because there'll be no way of enforcing anything, but obviously they will model themselves on certain manners. Well, yeah, okay. It's all very well to say that's still a long way off, but it is going to come some point. And really, as we've discussed with this, the best time to sort it out is before it happens.
Yes.
Now, how long will it be before these mega constellation owners claim a benefit of the shield of satellites is that they reflect sunlight away from Earth, thereby helping reduce climate change impacts? Well, the thing here is that your visualization of the satellites, although very dramatic, doesn't really show them to scale.
No. If you remember from my table, the diameter of the satellites is going to be of the order of a few seconds of arc, 3 or 4 seconds of arc. So if you took all of the satellites and put them next to each other, you have probably a fraction of a square degree of the sky obliterated by those satellites. Certainly not enough to shield the Earth. It might not stop them trying to do it, but I don't think they get away to pronounce that is the benefit, but I don't think they get away with it.
Make a dart out of them. From Richard, mega constellation sounds like the new COVID-19 for space. Let's hope some or one of these organizations can get control before it gets out of hand. And John Collins, has the British government weighed in at all on this? Well, yes, with their state, big state state.
Yes, with OneWeb and their pretensions with OneWeb. I mean, OneWeb could be successful because, in a sense, they are going for the market of selling to the providers rather than the end user. So the likes of Vodafone and EE and BT and so on make use of OneWeb's services, not you or I directly.
Okay. I think we've had a good selection of questions there, and time is pressing on. So I think I'd like to ask everyone to thank Paul for a fascinating presentation, slightly disturbing one, I have to say. Let's hope that something can be done and we're not going to lose the sky. I mean, it's been bad enough. All kinds of things have come up presented as a benefit to us. You know, so like LED lighting is going to save so much energy. But the problem with a lot of LED street lights is that they are basically white light. Whereas with sodium lights, you can get a sodium filter and put that on your telescope. So you take your astrophotography and you can balance that out. If you want to balance out the white light, you're basically putting a neutral density filter over your telescope, and you're cutting out all the light that comes in. And so here's something else. Yes, we're being priced, oh yeah, great, low cost broadband, but you don't get something for nothing. And there are problems with this, which Paul has alerted us all to. So thank you very much.
Thank you.
Yes.
Thank you very much.
Yes,
just one little return to the comment I made at the very beginning on Martin's talk. If you have the point of perihelion, of course, is when the barycenter of the Earth-Moon system is at perihelion, not when the center of the Earth is at perihelion. So if the barycenter is at perihelion, you could have the center of the Earth actually closer than the perihelion radius, or you could have, because the Moon goes round the Earth or round the barycenter, you could actually have the Earth's center being closer to the Sun, either side of perihelion. It's a real exercise in pedantry, however.
Yes, my Dr. Nitpicker would delight.
Yes.
Okay, thank you again. I think Alan's going to say something about next month's talk, but I would just like to mention something that came up in an email recently, that next month is the National Star Count. There will be something in the newsletter, next newsletter about it, which will come out just before the Star Count starts. Also next month, of course, we have 3 space missions arriving at Mars, and my granddaughter and I will be landing on Mars, as our names are on the Mars 2020 Perseverance rover, so we're looking forward to that. Okay, and with that, over to you, Alan, to finish off.
Okay, thank you very much there. It was an absolutely fantastic talk. I enjoyed it very much indeed. So thank you very much for giving it, Paul, and thank you very much, Jerry, for organising it. Just a few messages to give out to you. The first one is to thank Paul for the PDFs of the slideshow that we've had this evening. They will be available on our club website when we put the video link up to YouTube, so they'll all be in the same area. Next month, February the 10th, we have got 4 presentations for you. The University of Hertfordshire are providing 4 speakers. We're going to talk about various subjects. I won't go into the detail at the moment, but needless to say, it's actually already on the website. So if you want to go and have a look, we're going to look forward to hearing from John Collins, Caroline Devereux, Zen Guo, and Joe Ramasori. Something you can do as well, there's information on there about the Star Count for this year, Star Count 2021. Takes place between the 6th and the 14th of February. It sounds almost like you've got a choice, doesn't it? But I'm sure that's the choice is whether you can see through the clouds or not. Again, there are links on the website where you can register. Last year, it was looking at the constellation of Orion to see how many stars you could see with naked eye from where you live. And they haven't actually said it's going to be Orion this year. They haven't disclosed where it's going to be. Maybe it'll be somewhere else. But do have a little look, register for it, and you can take part in that. So that's February the 10th is our next meeting here, and 6th to 14th of February for the Star Count. I'd like to say thank you to everybody for coming along this evening. We had 46 people at one time, all looking in. So thank you very much. If it was your first time with us, we hope to see you again in the future. And all I've got to say to you all is thank you very much for coming. Have a safe journey home. Thank you and good night.